So our second talk is about verifying a compiler for Scheme, and the talk is given by Pascal. Yeah, please.
Compiler that we built called Brack. The name Brack is supposed to be short for barn brack, which is a kind of Irish fruitcake, which fits into the theme of cake-based compiler names in the CakeML ecosystem, which Jeremy came up with that name because he's quite good at making names for things. So just a quick summary of the whole thing. Brack is a verified Scheme compiler. It's written in whole for the whole for proof assistant, which is the same as what is CakeML is written, and the reason for that is because we're building on top of CakeML by targeting that ML, and we compose our semantic preservation proofs, which I'll explain in a second. To our knowledge, it's the first verified compiler which supports dynamic typing and first-class continuations, and it compiles using a continuation passing style transform, and I'll explain kind of the motivation for that. And so, firstly, just to quickly explain what verified compilation is to those who may not know. You're implementing the compiler in a proof assistant, and then what that allows you to do is if you have the compiler definition and the semantics defined within the proof assistant, you can use those together to construct a semantic preservation proof. And this is roughly the shape of that sort of proof, which I've left deliberately vague because the specification is kind of flexible. At a top level, what you want is to have the observable trace of execution of a program to be conserved from the source semantics to the target semantics. And then kind of at a more specific level, which this diagram sort of represents, like in the case of our semantic preservation proof is a simulation proof for Scheme. You'd have reductions. This basically is supposed to say that reductions in the source and target semantics should be the same before and after compilation. And I've also left those squiggly arrows to be a bit ambiguous because that can either be actually the compiler or it can be a relation that the compiler satisfies, and then you make sure that square commutes. And then an important part is that you can compose these semantic preservation theorems, which is exactly what we do by composing our semantic preservation proof from Scheme to ML with CakeML's existing proof from ML all the way down to machine code, and that's how we get a complete verified compiler. And so this is not, in light of the last talk, this is not a political choice. Our Brack is based on the formal operational semantics from the 6th report. There's not really much of a particular reason for that. The reason why I chose it, I think, is because it was easier to kind of extract like a subset, the small subset that we wanted to target from the 6th with the operational semantics rather than the denotational semantics. And this basically is the subset. It's not very big. Importantly, it has lambdas and call CC and lists, so you can express some interesting list like data processing operations, immutable lists, but lists nonetheless. And Brack performs a single compiler pass from Scheme to CakeML, which involves a continuation passing style transform. And kind of the point of all of this is that the naturality of the CPS transform is what makes the semantic preservation proof kind of, in a way, easy to do. And this is no coincidence. You can effectively arrive at the CPS transform directly from the specification of the small step semantics. This really came from Danvi's work on refunctionalisation. We use that idea to take a CEK machine or CESK machine to arrive at effectively a CPS definitional interpreter. And what you end up doing is, if you think kind of like partially evaluating that over a program, and then you end up with an AST, and that, in a sense, is a compiler. It's not a very efficient compiler, granted, but it is easy to prove, and that's kind of the purpose of this work. And yeah, so basically, with that line, it becomes, semantic preservation becomes a matter of proof of correctness of refunctionalization, and then proof that that partial evaluation kind of embedding into ML is also reasonable. And so I want to give a tiny example of what that kind of looks like. I especially want to kind of, yeah?
You said the naturality of CPS makes the proof easy.
Yeah.
Is it because it's compositional, so we can just do a proof by induction?
It's not even by induction. We just do it because we only do like a simulation proof for each step, and then we can just do a case match over all of the steps. And so I'm going to give a kind of example of what this refunctionalization looks like, which I'm sure a lot of people are probably familiar with, but I'm explicitly adding assignment and mutability into this example just to kind of show how, as you start to add different language features, how you can adapt the refunctionalization technique to a language. And I've chosen to use a CES-K machine. It works really nicely with refunctionalization, mostly existing CakeML in ecosystem uses this style of small step semantics. So we're following on with that. And lambdas don't take lists. They just take a single parameter. So you could probably, this is basically just like a call by value lambda calculus with mutability and assignment. And so this is what the CES-K machine looks like. I hope this is not too surprising to anyone. It's a call by value lambda calculus, but instead, when you continue with an application, rather than just binding in an environment to a variable, you bind to a fresh store location. And so that is how you can then use mutability. And then set is the expression where here you change the value in the store. And so refunctionalizing this, you'd end up with a CPS definitional interpreter, which looks a bit like this, which again looks quite similar to the call by value lambda calculus one, but we're instead using a store and doing fresh allocations. And so what you can then do is this is the same definition basically, but I've just shifted things into some lambda abstractions. And then I'm going to color it pink, just to make the difference to say this is no longer like the defining meta language that we're using to define the interpreter. We're now saying this is ML, we're compiling to this is an AST, and then the blue is the scheme, the pink is the ML, and then the black is the defining meta language. This is not actually, and this is basically what I mean by we're doing it like a partial evaluation over the scheme program. We want to expand it fully over the scheme program, and you can't actually do it right now with how we've just directly done it. Maybe you might be able to see why. The reason why is because when we try to expand over this expression doesn't actually exist yet because we bind it inside of a continuation closure. So this isn't actually a compiler yet. Turning it into a compiler is a matter of moving that transform up into the definition of the lambda expression itself. So that should look familiar. And then this is basically a compiler, but it's quite bad because we have the simulated environment and store we're carrying around, which is redundant. And the reason why is because now that we're in ML, we actually have access to refs. So we can do mutability basically directly with direct compilation. So the first thing you can do is get rid of the store, and you have a slightly less bad compiler where instead of doing the fresh location allocation manually, we're just using the ref syntax, and that does everything automatically. You have to dereference variables, and then assignment basically comes very easily where you just sequence an assignment from ML. And then you can get rid of the environment, which is a case of Scheme and ML share the same lexical scoping, so you just use variables directly in ML. And then you arrive at basically the Plotkin-style CPS transform with the slight difference of you're using references to enable mutability. And this is just like an example with a very small scheme with mutability, and I hope to convince you that this technique scales, and you can apply it to a larger scheme, like the scheme that Brack supports. You can use it to compile control operators like call CC in a continuation passing style, and with all of that, you still get the same benefits, basically, of the simulation proof, and semantic preservation proof becomes, relatively speaking, quite easy to do because of the naturality of this derivation. And so, to summarize, Brack is a complete verified compiler for Scheme, and that subset includes call CC. And we use refunctionalization to derive this CPS transform, which is effectively correct by construction from the semantics directly, and we can apply this to a larger language from this example, and that includes call CC, which ends up actually, funnily, either surprisingly or not surprisingly, is the easiest part of the compiler to prove. And so, yeah, that's made simple. So, thank you very much.
Thank you.
Thanks, great talk. I understand what you did. Can you backtrack to the point where you introduced the store?
Yeah. So if you were putting the store last, then you could eta reduce the store, and then it would kind of disappear. And then the only place where you need it would be since it's all tail calls, it's almost like a monad, a state monad where everything is implicitly eta reduced,
right,
and you need one operation. So there's no need to be as explicit as you did if you put the store last, because then you can eta reduce it, and now you have something in CPS.
Okay.
So there's nothing to invent there.
Okay, that's
and the proof should just small things to change.
Well, one thing I should clarify is that we don't, like, this definitional interpreter doesn't actually exist within our proof, basically. I'm using it more as an example of showing how you arrive at the final, like, these are mental steps that you take. But because of the way that you can arrive at it through this process, you can be confident, basically, that you can do the simulation proof and it will work. This is often just the issue with trying to verify something, is if you just make a compiler and then you verify it and you're like, I don't know if this works actually, and then eventually you find something wrong with it. Making sure that you derive it from this sort of system means that you can be sure that as you're verifying it, as much work as that still is, it's still laborious, you can be confident that it will work. And if it doesn't, you did the derivation wrong and you need to fix it.
Okay, that totally makes sense. But if you swap the sigma and the kappa at the top, it gives you lambda, rho, kappa, sigma, and then you can eta reduce the sigma, except for the operator that needs it. Okay, and so the sigma goes away from everywhere, it disappears, which is, as Peter Moses was saying in his talk, is also used in the semantics of scheme, where there are lots of things that are not there because it's curried and eta reduced.
Oh, I see. Like the denotational semantics?
Yeah, for example.
Okay, I'll need to take a closer look. Okay, thank you.
All right, thank you very much.